Let's just take a brief look at some of the factors that go into doing tropical cyclone predictions. Of course, you have to predict the motion and intensity, rates of intensification, amount of rainfall expected, and so on and so forth. And we've already talked about this beta gyre steering of the cyclone. Even if there is no environmental background winds, the fact that it's a cyclonic circulation moving from low latitudes to high latitudes on the western side of the in the northern hemisphere and moving towards the equator on the east, moving away from the equator on the eastern side, moving towards the equator on the western side, we create anticyclone cyclone beta gyres, which steer the cyclone at 2 to 5 meters per second, and then environmental background, environmental relativity gradients, and so on, make the things much more complicated. So steering winds obviously have to be captured by the cyclone prediction model. So here it is combining steering and propagation to estimate TC motion. So you have recurving in the southern and northern hemisphere. So here is the equatorial equator with tropical easterlies on both sides, the trade winds. So if you have a cyclone that's just formed in the tropics and heading, it's in the steering wind of the northern hemisphere, the beta gyre steering is going to be to the northwest. So the total wind steering the cyclone are going to be towards the northwest in this direction. And if it is recurving and maybe transitioning to extratropical cyclone, or just getting re-steered within the tropics itself, then you have you may have background winds that are westerly, and you have the beta gyres still driving it towards the northwest, and you have the net steering winds showing up here, and you of course change the whole story moving towards the southwest, or sorry about that, southeast, depending on whether it's being born and growing or recurving. You can add these winds. So here it is tropical cyclone steering flow from mean wind. You typically look at mass weighted winds here from 850 to 200 hectopascal. So we are looking at schematic of TC motion resulting from steering and propagation in easterlies and westerlies in the northern and southern hemispheres. In the second figure, we look at hypothetical storm motion vectors resulting from the linear sum of the climatological mean winds, mass weighted over 850 to 300, with propagation for each latitude for the same TC added. So here the mean TC recurvature paths are shown. So you can see the equator is here, easterlies on both sides. Let's focus on the northern hemisphere. So the steering winds mass weighted are shown here with the cyclonic circulation added. So you can see the addition of the counterclockwise circulation and the recurving winds happening here as well, and the other way in the southern hemisphere. So most models are now getting better at doing the tracks. We will look at the models that are used. There is a statistical model which does it as well, which obviously doesn't allow the cyclone to evolve along the way, just uses the winds given the intensity of the cyclone. But when we come to that, we'll see what we mean. But a real dynamic model obviously has to evolve the environment with the impact of the cyclone on the winds themselves, because it's not a passive tracer being affected by the background winds. The vertical wind shear impacts are very critical, of course. We are showing here a weaker cyclone which is greatly affected by the vertical shear, environmental shear, whereas the inertial stability and the resistance to the shear is much higher when the cyclone has got a stronger circulation, maximum sustained winds, stronger eye and eye wall, and so on. And the distortion of the eye wall is also going to create convections ahead on the down shear side, and then create asymmetries, and then the cyclone has to resymmetrize before it can re-intensify, and so all kinds of details would be involved in the vertical shear background. The other thing that obviously affects the tracks is the so-called Fujiwara effect, or the Fujiwara dance as we called it. And here is an example of multiple storms that potentially can interact with each other depending on the distance between them, which we said is critical at about 1,000 to 1,300 kilometers when they can feel each other's winds. So here is Tropical Storm Louis, Karen, Iris, Umberto, and so on. So all of them enhanced IR is mapping at 11:45 UTC on August 29th, 1995. So we can look at relative positions of Iris and Karen, illustration of the Fujiwara effect here. So the relative motion of Iris on this side with respect to their centroid, and relative motion of Karen here with respect to the centroid. So relative tracks of 1995 North Atlantic Hurricane Iris and Tropical Storm Karen, tropical storm and hurricane. Note how the direction of rotation changes from cyclonic to anticyclonic as Karen is eventually absorbed. So we have counterclockwise circulation coming in that is being entrained by Iris, which is the stronger of the two, and it's going to get it's going to absorb Karen into one. You can see that they can merge, they can escape, or they can just go around each other depending on the strength and the distance, and so on. What are the factors affecting the tropical cyclone intensity change? We talked about potential intensity, which depends on the sea surface temperatures. Not every cyclone will reach its full potential intensity. Intensity change also happens when it moves into colder water, or touches land, or makes landfall, or there is vertical shear, and so on. This is a schematic of the upper tropospheric factors affecting tropical cyclone intensity change. So the upper tropospheric factors affecting tropical intensity when it is intensifying, you have the anticyclone to the west, and you have the cyclonic circulation to the east. So this is the upper level, remember, upper troposphere, remember. So there is the 1,000-kilometer radius. So the outflow is obviously anticyclonic, as opposed to the inward bound cyclonic circulation near the surface. And you have open streamlines when the cyclone is strong and intensifying, and you have this strong outflow happening here. This is shown here as 20 meters per second. So large radial extent of strong winds outward from outflow jet axis, weaker winds downstream of the outflow jet speed maximum. So obviously the strongest of the winds for a warm core tropical storm are near the surface, and the upper level you have much weaker winds. Sorry, this should be non-intensifying. For a non-intensifying cyclone, you have unidirectional southwesterly, so the impact of the cyclone's anticyclonic circulation is not so strong here. Unidirectional flow near or over the center as well, and small radial extent of strong winds outward from the flow axis. Similar wind speeds, but you can see the open streamlines are not there. These are much more closed streamlines. Strong winds downstream of the outflow jet stream, and you have this complete recurving of the circulation when it's not intensifying. Basically, these are the factors that affect the intensity of the cyclone as it's propagating and interacting with the environment and with the surface enthalpy exchange with the ocean. whether it's warming and intensifying or cooling, surface is colder and the hurricane is weakening and or being affected by the vertical shear, and so on. The intensity and size are not always directly related, as we saw. The size, we said a larger cyclone propagates faster, even though it doesn't say much about the speed. Satellite image, or sorry, the direction. Satellite imagery of Hurricane Floyd and Andrew as they approach Florida here. So you remember sorry about that. You remember that we talked about the radius of the 34 knot winds to estimate the cyclone size. If it's big, it can be weaker, but the impacts can be spread over a larger region. So the evacuation plans will depend on whether it's a strong cyclone, but you are going to escape it, or it's maybe a weaker, larger cyclone, but you are going to get affected by the winds. So multiple factors determine the forecast and the warnings that have to be issued and so on. So this is at these times the two storms had similar intensities but very different sizes. Clearly the potential area of damage from Floyd greatly exceeds that of Andrew. Okay, so it's a nice tight smaller size cyclone with the similar intensity, but this one is much larger. So the prediction model has to be able to do this. As we will see, there are global models and then there are regional models, and the regional model, which means it is forced by boundary conditions at the edges. So the boundary has to be chosen far enough away that it can contain the cyclone completely within it. Otherwise you're going to have boundary effects and so on. Okay, so those are kind of the factors we worry when we think about the prediction of track and intensity. We will look at other details in the next podcast.